Welcome to my talk about SMB witness service in Samba. My name is Stefan Metzmacher. I'm on the Samba team and working for SerNet, doing development on Samba. So the topics for today are a brief overview over what the service witness protocol is, some examples, how it works, the design I choose for the RPCD witness used in Samba, then some strange things Windows clients are doing, how to configure the RPC daemon, and then an overview over the net witness commands to administrate things. So first, the service witness protocol is a way for clients to notify or to notice that cluster nodes in an SMB cluster are down or not available. And it also supports doing planned moving of clients to other nodes and so on. So basically it's on network interfaces or on whole nodes and for planned downtimes. The protocol itself is independent of SMB3. It's just based on DCE-RPC over TCP, and it uses Kerberos or NTLM-SSP for the integrity protection. So this is a capture showing the basic workflow. So the client is using the SMB protocol to start the negotiation, moves up to SMB2 here, and basically that's the same as SMB3. Continues, the client does a tree connect to the IPC dollar share, and then the tree connect to the desired file share. And the tree connect response includes some flags in order to notify the client that it supports continuous availability, scale out, or cluster. I will come to that, to the meanings of that in a later slide. From there, the client goes and calls the get interface witness command on the same server. It connected with SMB, and that returns a list of IP addresses which can be used to ask another node for monitoring. Then it switches over to a different node, 166 in this case, and registers its current connection. Basically the network name of the cluster, that's basically the same as in the tree connect. And then the IP address it's currently using, the 168. And then it gets back a response with a policy handle, and that is then feed into the async notify request, and that sits there and loops over. I think the timeout is 2 minutes actually, in order to notify dead connections in a better way. So basically it sits there every 2 minutes and refreshes that registration. Yes?
So is there actually theoretically a race between getting the response, someone changing an interface, and then the async notify request?
Yeah, sure. There are no guarantees. Yes, sorry. So the question was, is there a potential race between getting the list of interfaces and then registering with one of the IP addresses?
No, I meant the async notification. Once you send an error timeout response, you don't have any pending async notifiers.
Oh, okay.
The interfaces changes then before you get the next request.
Okay.
Is that a race as well?
So the question was when the client gets the async notify with the timeout, and if there's a race between that time and the next async notify request. And no, there's no race because the responses are buffered on the handle, and if you wait 2 minutes and then do the async notify again, then you will get the one you have in the queue still. One more question?
Yes. So what enables this buffering? What is the original? Like is it just the register? Which
Yes.
The queuing up.
So the question was what enables the buffering, and it's the register X, or in older versions the register function, and that creates a policy handle, and everything is so that's basically the state for all this, and that queues the responses which are not delivered to the client yet. So now we see what happens if actually the witness server notices that a resource is changing and how the client reacts on that. So basically the same as the last capture, up to the tree connect, and get interface list to get the IP addresses, the register X to set up the registration, then async notify the first times out, the second sit there for 11 seconds, and then the server responds with resource change and says the resource isn't available anymore, the IP address with the 167 at the end, and that means the client directly schedules an async request again, and then in the background also disconnects the SMB connection, reconnects to another IP address. And the thing is that, so you would assume that at that time the Windows client would do a new registration, but sadly that doesn't happen. So I had to do a trick there. So 5 seconds after we send the resource change, we answer the async response with W error not found, and that causes the client to unregister and then register again. So otherwise, even if a client already changed to a different node, the original registration was still there and never refreshed, at least for a few minutes. And it's very confusing if you see that in the net witness list command, which I will show later. So in order to have a consistent view and be able to move the client or let the client notice resource changes, we need to do that trick in order to have the client do a new registration with a new IP address. So the last slide, one question? Yeah. Yes. I don't know. I mean, it's not really important, I guess. So because it's just some helper protocol there. So it doesn't influence the behavior on the SMB client, but you will just not be able to move clients or whatever. But I wasn't able to set up a Windows cluster to test how a Windows server is doing this. So all I did was having that server on Samba and implement it as much as or in order to make the Windows client talk to us and do reasonable things. So here we have now the situation where the administrator tells the client, please move to a different node. Same as before, up to tree connect, get interface list, register X a few times out on the async notify, and then you get the client move command saying, please move to the following IP address, and basically the immediate async request again, and then the client moves to that IP address and doesn't re-register itself again, and we have the hack after 5 seconds there and to get things cleaned up again. So the design of the RPCD witness daemon in Samba, we had a few rewrites of the Source 3 RPC server in the last years. So basically before we had 2 independent infrastructures for being an RPC server. One in Source 4 for the Active Directory stuff, and in Source 3 for the file server stuff. And Samuel was so kind to merge that, and we now use the basic Source 4 infrastructure as a common code and use that in both implementations. On the top to the implementation of the services, this is still a bit different, but the core packet handling and so on, that's shared between both. And then Volker was so kind to isolate or having isolated RPC binaries for different services. So we have the Samba DC RPCD helper process that either starts RPC services on demand, but here if we want TCP support, we need to disable that, and the system control or ctdb needs to start the Samba DC RPC master daemon, which listens on the socket in order to serve IP TCP for Source 3 stuff. And with that in place, it was relatively easy to also implement async responses at the RPC layer, because at least for witness, we don't care about any user impersonation, because we don't work on any files in the file system or whatever. We just operate on database entries within Samba's own database. So in the past, we had some witness prototypes over the years. I think this was the first one was 10 years ago or so, and then in the meantime, other ones were created, but some missed the important interaction with ctdb, and one of them tried to implement way too much within ctdb itself. So I looked at all this and tried to find a way to take parts of it and combine them in order to get something that will work. But then I found that I really only need to be notified by ctdb if it changed some IP addresses. So it doesn't need to tell me what changed. It does need to notify me. And with that, I was able to have a very limited change in ctdb itself. And all I do in the RPC daemon is that I query all interfaces from ctdb, wait for the IP relocated notification, and then load the IP addresses again, and then I compare both lists and in order to work out what changed and what not. So yeah, that's basically, we load all IP addresses at start, wait for the IP relocated, and yeah, reload everything again, and then we are able to notify the registered clients. So as said before, because we need IPTCP, we need to disable the on-demand helper stuff. And yeah, we also register the TCP connections with ctdb's TCL infrastructure. That means if the RPC witness daemon on a node that's dying, a client will get TCP resets from another node in order to do or notice the disconnect very early instead of waiting for timeouts. So the register X results in a global registration. We have an RPCD witness registration TDB that's handled by ctdb. So all nodes see the consistent state of that. So yeah, and each registration creates a context policy handle as a key, and within the data it stores the server ID. That's basically the node ID plus the PID on the node in order to route the messages between the components. And yeah, that allows the net witness command to list the registrations because it just needs to enumerate the TDB. And yeah, for commands like client move or so, looking up the record in the TDB gives us the server ID, and then the net witness command can send a message to that RPC process, and that will forward the changes to the client actually. So there are strange things Windows clients are doing. One thing I already told you, that we need the re-registration hack, but this is also some strange things regarding the flags in the tree connect response. So as I said before, we have the continuous availability, scale out, cluster, and asymmetric flag. And basically the cluster flag is the one that should indicate to the client that a witness service is available. But the thing is that a Windows client will only use it if it also sees the continuous availability bit. Otherwise, it won't even try to use the witness service. The scale out bit means that there are more nodes active at a time. So that's basically always the case with ctdb. So we will always send this along now. Yeah, then the continuous availability bit, and that basically says that the share is always available, and the client should try to reconnect maybe to other nodes very fast and use very short timeouts and so on. And it also triggers the client to use persistent handles, even if the server doesn't support persistent handles. So that's the other strange thing there. And as we don't support persistent handles, we will get the request for persistent handles, but will never grant it. And each open will then generate an event log entry on the client, which is, I mean, it doesn't impact the behavior, but I guess it's not so nice to have a flooded event log with messages for that. Then we have the asymmetric bit, and that's used to indicate that clients should connect to different shares and might use different nodes for the share. So basically, if you have share A, you can connect to node 1. For share B, you can connect to node 2. And on the client side, this is more or less completely independent and have different TCP connections and so on. So in order to reflect that in the witness protocol, the register X command has optionally a share name. And yeah, question, Jim?
Is there, just to clarify, how does this interact or not interact at all with multi-channel? So if you have multiple nodes active, multi-channel is still only going to go to one IP address, correct?
No.
Smear those out across different
Yeah. So the question is, how does this interact with multi-channel? And Jeremy asked if multi-channel is still only against one IP address, but that's not really correct. It's still only towards a single node, but it can be multiple IP addresses of the same node. But yeah, if the client connects, it asks on the SMB connection for all IP addresses available for multi-channel, and the node will only expose its own IP addresses. Yes?
Can this also be used for cases where on a single node the IP address changes on the interface? Can it be used for that as well?
So the question is if this could be used on a single node in order to let the client know if IP addresses changed. In theory, I would say yes, but I don't really think it makes that much sense. But, I mean, I think it could be done, but I mainly focus on the ctdb case. And I only use the single node thing for my first experiments in order to get a Windows client to do anything at all. But later I switched to only testing ctdb. Yes, so next slide. Yeah, as said before, when the async notify response is received by the Windows client, it reacts on them, but it also reconnects the SMB connection, but doesn't re-register the new connection. And yeah, as said before, we use the trick to send status not found 5 seconds after the resource change. So the basic smb.conf to activate the RPC witness service is this one. As said before, we don't want the on-demand helpers for RPC, so the Samba DC RPCD needs to be started at startup in the same time as the SMBD and WinBind and so on. And we need to specify the share capability, continuous availability, explicitly in order to let the client use witness at all. But I said before that lets the client trigger event log entries for each open, which might not be that nice, and that's why it's not on by default. With this comes an ctdb event script in order to let ctdb start the Samba DCE RPCD in the same way as a winbind and SMBD. And now we have a look at the net witness commands. So the net witness list is basically a command that lists all current registrations. It basically enumerates the TDB. With net witness client move, you can send move requests to specific registrations, or even have no filter and send that to all registrations. So basically we enumerate the TDB and then filter each entry. And if there's no filter, we will send the move command to every node. Then we have the same for share move when we have the client having registered a single share instead of just the net name. Then we have a force unregister command that basically means something like the hack we had with the 5 seconds delay, but you can also do that at administrator and trigger nodes to force a re-registration. But it's mostly for debugging also. Then we have the net witness force response command, and that's basically used for testing. It takes a JSON input, and basically you can construct any async notify response you want and inject that for testing. So now we have an example output of the net witness list command. On the top you see just a single registration with a registration UUID. That's basically the UUID part of the RPC policy handle. You have the net name that was used in the registration, the empty share name in this case, the IP address that should be monitored, and then the client given client computer name. So it's basically up to the client what's displayed there. So clients can lie there. It's not checked in any way. Then we have the same output in JSON, which has much more details. You see details about authentication, the client account there. You see, for example, that the account name is the computer name with a $, at the end. So even if, one question, Günther?
One question, the timeout from the connection unity on the is that something that can be controlled? So this is referring to the timeout the client takes for
Yes.
the async notified, right? So
I'm not what. Yeah. So the question is the timeout is that, or if this can be controlled in some way. As far as I remember, it's part of the register X request that specifies the timeout that should be used. Yeah, so Günther says he assumes that with a lot of clients this could be quite noisy, but yeah, for each client, 2 packets every 2 minutes should not be that much. when you compare that to a highly used node where reading some files would generate thousands of packets per second. So what I was referring to before is that the computer account is used as for the authentication and the witness connection. So even if the administrator or some user mounts a share, then the witness connection is still made as the computer. And that also implies that this only happens if the client is joined to a domain. So otherwise, I don't think witness will be used at all.
An enterprise storage system that is currently on the market today allows them to go up to...
Then some examples for the client move command. Basically, you specify the witness registration ID you found first by doing the witness net witness list, and then you can specify witness new node equals 0 in order to basically the client will then get an array of IP addresses with all IP addresses of node 0 and can then choose to connect to any of it. And in the second, it's also possible to say witness new IP and specify a single IP address there. It's not in the examples here, but here you can see that's extremely useful for testing. If you have just one client or so, you don't have to look up the registration GUID every time. You can just say witness applied to all, and then the move command will apply to all registrations without specifying the specific one. And that makes it very handy for testing things. Okay, all this is part of the 4.20 release, and I mean, it would be great if Windows could fix the client and only use the persistent handles when the server said persistent handles are used, and not flood the event log. Or maybe just generate one event log entry per share mount or so, but not for each open. With that, I'm done with my presentation. Any further questions? Yeah, in the back.
Lots of times when we come up with a set of very one way with people run a basic optimization rather than doing development search on it. We will run a third running test and say, there's no so let's start running more of it.
Okay. Let me come down, it's too noisy there.
So from multi-channel again, the cost factor is if you're fixed on cost, if you're fixed on cost, then you can start optimizing other things as well.
So the question is, given that premise, if ctdb redistributes the public addresses, so say you have multiple addresses on one node, and you have multi-channel working on that node, and then ctdb moves the IP addresses so they're spread across multiple nodes, wouldn't that break multi-channel?
Okay, there you go.
That's my question.
Okay, well, thank you very much for your time, and please raise the question.
So the question was regarding the interaction of multi-channel with movable public addresses managed by ctdb, and if one IP address is moved to another node and how does this impact multi-channel, because with the current multi-channel design, we have a single SMD process serving multiple sockets, and that can only happen on one node. And the thing is that we notice or ask ctdb about all public IP addresses which are movable, and then if we have a connection based on that IP address, we will just mark the connection as such, and if that connection is either teared down by a notification by ctdb or by a TCP reset or so, then we close all connections so that the client can then do a fresh start on the other node. And typically in the setup with having multi-channel, you may also have public IP addresses, but separate ones which are local to a node. So basically, if you have 3 nodes and 3 IP addresses which can move, you may also have for each node 1 IP address that doesn't move. And the query network interfaces, which is used for multi-channel, will only report IP addresses which are not movable. So in theory, if the client only looks at the
You rely on the query network interfaces. Just not report IP.
yes, exactly. So we only report non-movable IP addresses in the query network interfaces, and then the client should only do multi-channel to those IP addresses. Any further questions? Okay. Thank you very much.